Welcome to this new episode of the arXiv paper pitch. This time I'm going to talk about the geodesics and quantum gravity. My name is Benjamin Koch, and this work has been done in collaboration with Angel Rincon and Ali Rihainia. General relativity is a wonderful theory that is supported by numerous observational tests. Perihelion shifts, gravitational lensing, Shapiro times delay, to name a few. Interestingly, all these observations involve geodesics one way or another. Thus it is fair to say that the beautiful castle of GR rests on the shoulders of geodesics. In our paper, we address the question whether the validity and the generalization of the geodesic equation in the context of quantum gravity can be made. Geodesics describe the motion of test particles in given geometric background. The corresponding equation has two ingredients. First, a test particle, described by a position, and second, a background metric, appearing with derivative and contractions in the connection gamma. It is interesting to note that actually this is not an exact equation for physical objects, but it's an approximation. So the object has to be very rigid, light, and tiny in size when we compare it to the size of the gravitational curvature scales. Or, if you remember that particles are actually waves in quantum mechanics, we have to implement this in terms of the so-called iconal approximations. Now, if these conditions are fulfilled, we can approximate the quantum operator of the particle x, take the vacuum expectation value, and replace it by the position coordinate of this particle. This is of course all well known, so in our paper we address something new. What about the second element in this geodesic equation? What about the nature of space-time? What about the metric tensor and the connection? Well, under which conditions we can approximate the metric operator by x expectation value? In our previous video we have explained that this transition to a classical metric comes with an intrinsic uncertainty, the uncertainty relation, and this uncertainty can manifest itself of course at very small scales, but also at very large scales, astrophysical scales, even astronomical scales. We have further shown that the VEF of the product of two metric operators is not equal to the product and then taking the VEF of these. Now, in this new paper we show that this distinction between VEF and products is particularly important when we think about geodesics and motion of particles in this background. And we reach the following conclusion. In the context of quantum uncertainties of spacetime itself, we have to first evaluate the operator product and then take the expectation value. This is not done in the geodesic equation. So following this new procedure leads to the q-desic equation as generalization of the approximate geodesic equation. We then calculate some examples. For these, we calculate, for example, spherically symmetric orbits, a circular motion around a central mass. And the classical relation, if you take the velocity squared as a function of the radius, we see that it's a decay of 1 over r line. But we now find that depending on the structure of the quantum space-time background, we can have deviations from this 1 over r law. There can be deviations at very small radial scales and at very large radial scales. This is indicated by the blue and the red lines in this graph. Now, of course, we can speculate the following. Think about the famous galaxy rotation curves, where the deviation of the 1 over r law and the velocity squared was taken as evidence for the existence of dark matter. Could it instead be evidence for the existence of local quantum properties of spacetime? We don't know, but in principle, we could fumble around with the integration constant epsilon of this spacetime and fit the galaxy rotation curves, as we have done here. But this at the current stage is a little bit too speculative, so we leave it at the following take-home message. The q-desic equation allows to describe the motion of test particles when you take quantum aspects of spacetime into account. This can, for example, lead to small deviations from the classical geodesic orbits at both small and large radial scales. Thanks for making it to the end of the video. For more details and feedback, check out the paper or leave a comment below.